Okay, so now we have to look at another chemical in our story, which is chlorofluorocarbons, otherwise known as CFCs. So CFCs were developed in the 1920s to replace things that were toxic and flammable in stuff like air conditioning, in refrigerators, aerosol cans, propellant, and solvents. Okay, so the reasons why they chose this chemical to do all of these jobs. So for these two here, it's because its boiling point is close to room temperature, and this means you do not need to compress the gas as much to get it to condense, so it makes it cheaper to run. Okay, aerosol propellants, because it's non-toxic, and it is also non-flammable. Which is really useful for the air conditioning and refrigerator units as well. And then it's used as a solvent because it can dissolve oil and grease, but it is does not damage electricals, which was less of an issue in the 1920s, but became progressively more and more useful. So used for like little things like cleaning dust out from under keyboards and stuff, all the way up to cleaning up delicate electronic circuit boards and stuff like that. Okay. And the reason that it had these properties were because it was quite a stable gas, so it made it really useful because it's non-toxic, non-flammable, and didn't damage stuff. Now, this was great until a couple of really important scientists came along. One was called Roland and the other was Molina, but they were part of much larger teams. And in 1974, they came up with a hypothesis which suggested that because of the chemical properties of CFCs, this meant that they could lead to depleting the ozone layer. So to lead to ozone layer depletion. So they looked at a family of chemicals, of which CFCs is one, and they found that CFCs are persistent. So the persistence of CFCs means that they are chemically stable. They do not break down because they're non-flammable, non-toxic, but this means they persist in atmosphere long enough to reach the stratosphere. So it had been thought that because CFCs were so heavy that they would remain in the troposphere away from the stratosphere. But it turns out they can last long enough that they eventually make their way up there through turbulence in the atmosphere. That if there is enough UV light, they will disassociate by UV and release chlorine. And chlorine is a really reactive gas. So chlorine free radical is highly reactive, and it's released in high UV conditions. Now, in the troposphere, you do not find high UV conditions. It's filtered out by the ozone layer. But high up in the stratosphere, that is exactly the location where the chemical bonds of the CFCs get broken by the UV light, releasing a chlorine-free radical. There is a reaction of chlorine and oxygen. So chlorine reacts with monatomic oxygen, preventing the formation of ozone. So you get this chlorine-free radical. It will bond with that monatomic oxygen, forming chlorine monoxide. And this means that there is no free monatomic oxygen for ozone formation. And it's worse than this because this chlorine-free radical will then be displaced by another monatomic oxygen to produce the chlorine-free radical and oxygen. So you can see that this can restart the cycle all over again. So it persists up in the atmosphere for a really long time, destroying ozone molecules or preventing their formation, sorry. And you also get other halogens. In this family of chemicals, so you get things like bromine and iodine, which can cause similar reactions. So you can't simply substitute chlorine for a different halogen.